My name's Fred Easy. I head up the analytics team here at SpaceAid. So, science the impossible. What do we mean by that? So, who here is a software engineer? Put your hands up. Okay, a lot of you. Good. Who here has worked at a startup or in a small team? Okay, and how many data guys have you got here? Awesome. Okay, this is perfect. Okay, so these talks are aimed at you guys. When we're talking about science of the impossible, obviously we're talking about things that are literally impossible, but when you work at a startup or in a small team, sometimes you're asked to solve very difficult problems. A problem could be something like building an infrastructure to support a real-time multiplayer game, where someone from China and someone from Australia need to play concurrently on a mobile device and not notice any lag or anything like that. It could be something like developing a complex machine learning model to try and serve different tailored promotions for players in the game. Lots of things like that, and these things are difficult. Like if you've got a small team, you've only got a few resources to rely on, and what we found here, and I think what you guys will find as well, is the most important things are being pragmatic and being creative, and those are the two things we're going to talk about today, and explain how those things work. So anyway, I've rattled on long enough, so without further ado, I'm going to introduce Tony and Jan, who are going to talk about big data challenges in real-time multiplayer games. Thank you.
Cool. So I'm just going to do an intro on this section. Jan's going to come and talk about kind of more of the juicy details of how we're doing this. But I'm Tony Yang. I'm product owner here at SpaceAid Games, and I kind of want to talk about why we are interested as a company with real-time multiplayer games. And hopefully, if you're a game studio as well, you can understand why 2017 might be a really good and interesting time to explore that as well. So jumping straight into the hard data. So this is some high-level stats about, if you look at the US top grossing chart on the iOS App Store, these are all the real-time multiplayer games that have been top grossing each of these years. So it started 2014, started pretty simple, turn-based games such as pool and card games. But you see it over time, especially 2017, it's kind of, we believe we're reaching some kind of tipping point with real-time games on mobile. If you maybe take out bingo and slot machine games for that 2017 number, we're approaching almost 20% of the games on the top grossing chart for in the US, having real-time as one of the core interactions of the game. And pretty certain that number is going to grow even in 2018. So what are some of the enabling factors? This is I'm sorry for all these charts, but basically the big four mobile networks in the US, you can see in 2015 the average download speed was around 15 megabits per second. 2 years later, that's doubled. So obviously connection speed, latency are less and less becoming barriers to creating games on mobile. Availability of 4G in the US is approaching 90%, and ping times on 4G networks in the US are well below 100. So this wasn't the case 2 or 3 years ago, and this is why 2017 is a pretty interesting time to be exploring this on mobile. Another factor we believe is touchscreen have been around for now 10 years, with the iPhone announcement being 10 years ago. And we believe that a lot of gamers that have grown up on the touchscreen generation are now reaching a period where they actually have pretty strong purchasing powers. This was 10 years ago. They're probably 13, 14. Now they're on their second or first job, for example. So a lot of these emerging trends around the technology, the hardware is getting better, network performance is getting better. A lot of mobile-first gamers are emerging, and now they have spending power. So all these things are coming together in 2017, and that's why it's becoming very interesting. We're seeing the reflection of that in the top grossing charts as well. If you look in Asia, they're way ahead. So all the top grossing games are multiplayer games, for example. Just a quick quiz. So in 2017, which of these games has made the most revenue? Is it the world's most popular MOBA on PC? I think most of us know what that game is. Is it the world's most popular first-person shooter? Is it some game by Blizzard? Is it some game by EA? Is it a Chinese 5v5 mobile game you've never heard of? Or is it some game by King? And obviously it's a bit of a trick question. It's actually that game. So this game you might not have heard of. It's called well, sometimes it's translated as Kings of Glory, sometimes Honor of Kings. It's made by Tencent, and it has 400 million monthly, over 400 million monthly revenue grossing, has 80 million DAU, and it's a full-blown 5v5 multiplayer game on mobile. It came out in 2015. They also own Riot, who owns League of Legends, for example, but just really interesting timing. This is just an example that not only can the technology scale to very, very mass scale, but can also be commercially successful potentially. At least in the East, that has been proven. So the technology is ready in 2017 for multiplayer games on mobile. I think you can see that both in the East and West. In the West, more so with Clash Royale and Golf Clash. In the East, very much proven so with this game, Kings of Glory. So that kind of wraps up my section on why it's interesting in 2017. I'm going to pass it back to Yang now, who's going to talk a bit about the technology to make that work.
Is this on? Oh, it's on. Okay, I can hear myself. No, great. So as an engineer, when you're trying to build a game like Kings of Glory, what you're really doing is you're trying to take a build application that needs to send and receive lots of data very frequently and are super sensitive to lag, and try to make it run on mobile networks that are famously or infamously unpredictable and also often with limited bandwidth as well. And your challenge as an engineer is to make these two pieces that doesn't quite fit together and try to make it work as best as you possibly can. And that often requires you to make decisions around various approaches that you can take to solve this problem. And whilst you want to optimize towards user experience, we know that the thing that has the biggest impact on user experience is the latency. So that means the decisions that we take are going to have to optimize towards latency. But being a startup, we still have to work within the constraints of cost, complexity, scalability, as well as how much operational overhead we're going to give ourselves. And the first question that often comes up is whether or not you should have a globally deployed infrastructure. Once you've got players playing your game worldwide, or using your app worldwide, one of the common approaches is to still put all of your infrastructure in one region, often in the US, because that's where you're likely to have the highest density of users for your app. And that's okay for most mobile applications and websites, where the network latency is not as strict a requirement, but where you're making a fishy real-time multiplayer game is not such a great idea. So typically, people in this space will be deploying the infrastructure all over the world so that you have servers as close to your users as possible in order to minimize the latency they're going to experience. So when I try to score these two approaches, try to compare them, I put them on the chart where the higher the score, the better. As you can see, I've penalized the, let's see if the thing doesn't work. Okay, never mind. You can see that I've penalized the cost for the global deployment because you're always going to incur additional overhead, overhead for every region you deploy to. But at the same time, you're going to win on the latency. And since we already discussed that in order to optimize towards user experience, you have to optimize towards latency, which is why we decided to go with the global deployment approach. So in this world, you will have servers deployed all over the world, and you will route your players automatically to the servers that are geographically closest to them. And when you start a match, you will also match that player with other players that are also in the same geographical location so that everybody gets the best experience possible. But since you are now segregating your user base by region, a bunch of other questions comes up around game design. So do you keep features such as leaderboards and the guilds regional, or should they be global? And what about things such as chat rooms and live ops events? And if someone really wants to play with family and friends that are living in a different country, should you allow that? And how would that support look like? Which brings us to the next question we have to answer, which is how we're going to approach the interaction between the client and the server. The two main approaches we looked at was first, server authoritative. So in this setup, the client or the server will run all the game engine or the game logic. The client will just send the inputs to the server. So on, say, 15, 20 frames a second, the server will broadcast to all the clients the latest state for the game, which could be a snapshot, or it could be a delta from the previous update. On the client, you would then synchronize the update from the server with your in-game, your local state, and whilst you're waiting for the next broadcast from the server, you will render the UI with some prediction so that you mask the network latencies as best as you can. In terms of interaction, the server is broadcasting state updates 15 times a second, but because there's latency, you don't get the user inputs in the same frame that they were sent. In this case, both the inputs from both players are received inside the first frame from the server's perspective, and they'll be used to generate the next game state and broadcast out to all the players. And again, when the player 2 is now sending a new input, you don't receive that until 2 frames later. So you don't observe the effect of the user input until 1 or 2 frames later, and that seems to be quite common. This is a very popular approach with games that run on desktop as well as a console, and some mobile games use this approach as well. And it's for a very good reason. It's quite a simple approach. Everything is always in sync. The clients are just reacting to game state changes from the server. And because all the engine, all the logic is running on a server, it also means the game is really hard to cheat as well. And the server can automatically detect when the player has been disconnected and then take over the player with AI behavior. The two main downsides to this approach is that you are putting a lot of logic on a server, so the load on the server is super high, and game states are quite big, even if you're just sending deltas. So you're also using a lot of bandwidth. And when I came to scoring this approach, you can see that I penalized it very heavily on cost, because more load on the server means you need to run more server, therefore more cost. But from multiple sources, we also heard the same story that at scale, your biggest cost is going to come from the bandwidth, which is why this approach is scored very low on cost. And because the client also have received more data, I also penalized it for latency as well. This is especially true when you're going to a country with a poor bandwidth, such as China, or in fact, most of Southeast Asia. The other approach we looked at is called the lockstep, and I would like to add that this is not the lockstep approach that's used by most real-time strategy games, which typically use the peer-to-peer model, where literally the client wait for updates from each other before they process to the next frame in the game. This variant, the client will send the inputs to the server, who will collect all the inputs from different clients, buffers them into, again, 15 to 20 frames a second, broadcast them to all the connected players in this game, just inputs from everybody else, including themselves. So on the client, you will play all the inputs in exactly the same order, so that everybody in the same match will always arrive at the same game state internally, so you get synchronicity. Again, when you're waiting for the server to broadcast the next set of inputs, you render the UI with some prediction to mask a network latency. This diagram looks pretty much exactly the same as before. The only difference being the server is now broadcasting user inputs rather than the actual game state itself. And we talked about latency before. I didn't mention that the latency that's important is what we call the round trip time. So that's the time between you, the client, sending an input to the server, to receiving back that same input from the server, which, as you can see from this diagram, depends on the network latency from the client to the server and back, but also the time at which the server receives the input in relation to when the next broadcast is going to happen. And this is the approach that the Kings of Glory uses as well. The advantage to this approach is that you're not running any complex game logic or simulation on the server. So the load on the server is super low, and since you're only sending out user inputs, which are typically a few bytes per player per frame, so you're also not using that much bandwidth either. And since the server is ultimately now just becomes the messaging hub, you also end up with implementation that should technically be quite reusable for different games. The main downside is that you now need to have a deterministic game engine on the client, which is difficult, especially when you're using Unity, because Unity has a long-standing problem when it comes to determinism for floating point math calculations. I don't know why this happens, but when you do math calculations, say in C# and it gets compiled to different platforms, the code that gets compiled to behaves differently. So the same math calculation would give you different results on iOS versus Android. So even so, when you in your game logic, small change you can start to compound, and you have what is known as the butterfly effect. Also, since the game engine, the game logic only runs on a client, so the game is now hackable, which requires you to still have some form of server-side validation, perhaps by running the game engine as a headless process on the server. And when someone gets disconnected, the server can detect that and tell everybody else that, hey, Haito just disconnected from the game, but all the clients would then need to take over the behavior for Hector's player in the game with AI, so that you don't end up with lopsided matches. Now it becomes, instead of 5v5, it's now 5v4. You do get 5v4 plus the bot, but still, it's a lot better than just 5v4. Also, when you join a match, the process becomes slightly more complicated and longer as well, because the new client now needs to consume all the inputs since the start of the match, and then catch up to date to the current frame before he's able to continue and really participate in the game. And because you need to make sure that all the clients in the same match is running exactly the same game logic, so that you get that determinism, you also need to take care in the matchmaking process to make sure that all the clients in the match are running the exact same version of the game engine. So with this approach compared to server authoritative, we are having to solve more complexity problems. We have to implement fixed point maps ourselves, and we have to implement server validations and so on. But in terms of cost, this is a lot better compared to the server authoritative version. And whilst for us, cost is a big consideration, we are a startup, we do need to make our games profitable. For Tencent, however, with the amount of money they're making from all their games, they probably don't care cost as much as we do. But I think they still chose this approach because, for starters, the 4G coverage in China is not very good. And when you consider the bandwidth for China, it's all the way down 74th inch in the world. And it's easy to forget that when you're in the West, we are very privileged to have really good, stable internet connection with great abundance of bandwidth. But when you're trying to build a product and try to attract a worldwide audience, you do need to design for those countries with poor bandwidth in mind. Which brings us to probably the biggest question of them all is, do we build our own networking stack, or do we use something off the shelf, something like something like Photon perhaps, which works very well with Unity, and as SpaceX Games, we have a lot of love for Photon. They've done a really good job in making sure the API is easy to use, and you get a lot of things out of the box. You get multi-region support, you have a fully working lobby system, and also we are already using it for many of our prototype games. Also, these guys have had many years of optimizing their networking stack as well to make sure it's as performant as possible. The downside to using Photon is that the pricing model can be quite expensive at scale, because the way it works, you're saying, okay, you need to pay for a reserve peak monthly CCU, which is concurrent connected users. When you're paying for peak load all the time, that means you're paying for a lot of resources that you're not actually using, and also there's a big penalty when you go over that provisioned peak throughput, monthly throughput. But for us, perhaps the biggest question is, as a company that's building more and more real-time games with a real-time multiplayer element, as Tony alluded to, 2018, is probably going to be the tipping point where you're going to have more and more of those kind of games dominating in the charts. Can we really bet the future of this company on a third party for a really core piece of our technology stack that's going to be powering all of our games? And it's for this reason, rather than anything technical, that we decided to hedge our bets and invest time and effort into building our own networking stack as well. And we built our networking stack on top of Akka and Netty framework. For those of you who are not familiar with Akka, it's a framework in Scala that allows you to program with the actor model, which is a model for describing computation, and it was coined by Carl Hewitt all the way back in 1973. And it was later on made popular by Erlang, even though the guys that created Erlang didn't set out to implement the actor model, which is a very interesting story. If you want to hear about it, come talk to me afterwards. Anyway, so in this model for describing computation, everything is an actor. An actor has got a mailbox, and they don't share any memory, so for actors to communicate, they do it by asynchronous message passing. When I receive a message from another actor, I have three things I can do. I can create another actor, I can process the message, do some useful work, or I can send another message to other actors who I have the address for. And the benefit of the actors not sharing any memory is that if one goes down, you don't have this cascade effect of taking everything else down with you that you often find with other applications, other systems, whereby one unhandled exception bubble all the way to the top, kills the process, game over. So it's a very nice property to have when you're trying to build a system with a high uptime. And when you talk about uptime, the magic number people always talk about is 9 nines. So that is, how do you build a system with 99.9999999% uptime, and only, so this is a system that can only go down for less than 31.5 milliseconds a year. Whilst you may think, well, that's like a magical unicorn, no one can build that. There's actually a very famous case study that showed well, if nothing else, the Ericsson AXD301 system, which is a telephone switch, that was written with 1.5 million lines of Erlang code, plus another 500,000 lines of C++ code. So the Actor system can help you build very highly resilient systems, and without the Actor, everything, messages are processed one at a time as if everything is single-threaded. Again, so where you have shared resources, you don't have to protect them with logs, which also simplifies concurrency management. So no logs, no deadlock situations involved with the use of logs. You can still have deadlock situations with your protocol, but we're not going to go into that details for now. With the Actor model, you are essentially lifting the concurrency management to the system, into the mailbox, so that I'll say that you can, so that allows you to think globally, but act locally, but I'll elaborate on what that means later. The key thing to know here is that it allows you, it's easier to think about a complex system in terms of state and transition, rather than how am I going to manage state mutations with logs and other concurrency control mechanisms. So in our system, you have a match. We've got a current frame where we are buffering all the user inputs, and I've got a full history of all the frames up to now, so that when someone joins halfway, I can just give them all the inputs, all the frames up to now. And when a new user connects to the system, opens up a socket, it authenticates himself with some special payload, and we can create a new event to the current frame that this new user has joined. And then once authenticated, this user can start sending and receiving inputs from the system. So we receive a new input from this guy, and now it's time to broadcast. So we take everything we collected so far and we broadcast to all the connected players over the socket. And we also then save that current frame, put it into the history, and start buffering for new frames, for the new inputs for the next frame. That all sounds pretty simple, right? Logically, it's actually a very simple system. It should be a piece of cake to implement, but anyone who's tried to implement this kind of system knows that the devil is in the concurrency. How do you manage a system where so much concurrency is happening all at once? For starters, when you try to broadcast your current frame to all your connected players, they're also trying to screw you over at the same time by sending you inputs when you're trying to send them stuff at the same time. And because you've got more than one player connected in one match, everyone's trying to screw you over at the same time, see who can get there faster. And guess what? You've got more than one room happening on a server at the same time, so this kind of race to screw you over just happened all over the place on a server. Now imagine in a different world where rather than the socket system, the sockets trying to mutate the current frame directly, instead they would send a message to the match to say, hey, I have just joined. Hey, here's a new input. Please include it in the current frame. And when the match tries to broadcast the current frame to everybody else, it also does so politely via message to the mailbox for each of the socket actors. So this allows you to, the presence of this mailbox gives you this bounded context around the various abstractions in your system. And bounded context is something that you probably have read about from Eric Evans' seminal book, Domain-Driven Design, where he describes it as a magical boundary around what is called root aggregates, outside of which everything happens via message passing. So even whereas you have a system where you have all these crazy concurrencies happening, while you're working inside an actor, you can still just blank everything out and focus on just a few simple things. What is my current state? What message have I just received? What shall I do with this message given the current state that I'm in? Of course, in order to understand how your system is working, you should understand how all the different actors interact with each other. That's where protocol design comes in. And being British, I fully appreciate any system that loves queuing as much as I do. But more than that, I love the simplicity with which I'm able to solve otherwise complex problems. And that simplicity, incidentally, is also what allowed us to very quickly optimize our implementation. And if there's one thing I want to take away from this talk, let it be this message, that the trick to building a highly performant system is simplicity itself, because what's complex is also going to be very hard to optimize. And in our networking stack, it's going to be the core, the gut of our multiplayer games. Performance is super important. The more players you can have per server means you have to run fewer servers, and therefore you have lower costs, and you give yourself less operational overhead to manage the servers that you do have. And for those of you who are engineers, you probably recognize that guy, that's Donald Knuth, and you may say, hey, why do you have a picture of Donald Knuth on the slide that's talking about performance? Isn't he the guy that says premature optimization is the root of all evil? Well, yes, he is, but chances are, every time you've been shown this quote in the past, you have been misled, because that is not what all Donald said. The second part of this quote is just as important, where he said, yet, we should not pass up our opportunities in that performance critical 3% of our system. So the next time you go to an event or a conference and the speaker shows you just the first half of Donald's quote and tells you to justify why they're not optimizing their system, please do me a favor and call them out for not doing their homework. So performance is important, and the active model can also help you build a very performant system, because fundamentally it doesn't use threads as the most basic unit of concurrency. Threads, they're great, but they're also very expensive OS constructs. By default, when you spawn a new thread, you also allocate 1 meg of memory space, which on a 32-bit system means there's upper limit on how many threads you can actually have. And when you have many threads all running concurrently, context switching at scale becomes really, really expensive. It's not unlikely for you to be spending more of your CPU time just context switching, moving things in and out of the register than actually doing useful work. And with the active model, actors are super cheap. Depending on implementation, in Erlang, actors are, I think, a few single-digit kilobytes size. I don't know about actors. I don't know about implementation detail for Akka, but ultimately, active system, they can optimize the number of threads you're going to need to use for this system in order to minimize the amount of context switching so that you can get more of your CPU time doing useful work. And Netty is non-blocking I/O framework for the JVM. It's highly optimized and it's very performant, and it really simplifies the task of implementing a socket server in Scala, in Java as well. But the UDP support is not so great. Again, if you want to find out more about it, come talk to me afterwards. It's something that I'm looking at actively right now. In terms of performance optimization, what we've done so far, nothing, nothing extraordinary. It's all the basic things that everyone would be thinking about. We've designed a custom network protocol in order to really minimize the amount of bandwidth that we use for our networking. We implemented buffer pooling as well as minimizing the amount of objects that we create with Netty and in our system in general in order to minimize the pressure we put on a garbage collector. And we also use Netty support for direct buffers. So this is where you will allocate your buffers onto unmanaged memory so that the garbage collector doesn't have to manage it and therefore feel less pressure on the garbage collector. Of course, it then falls down your shoulder to make sure that you do release those memories at the end, otherwise you end up with a memory leak. And in terms of TCP configuration, we haven't done an awful lot yet. This is one of the next things we're going to be looking at very closely. So far, all I've done is to disable Nagel's algorithm. So for TCP, the default behavior is that you will batch up small packets and you send them in a batch. In the case where we need to receive many small packets very frequently, this is going to hurt our latency. Therefore, we disabled the Nagel's algorithm. Another thing we did was we used EPO, which is a system call that was introduced into the Unix kernel to make those networking calls a lot more efficient. As part of our quest to optimize our system, we also put together an automated pipeline for load testing using Amazon Lambda instead of EC2 instances. And again, we got a whole bot client that's been written in Akka that we use to run our, automated acceptance testing locally. But we can then use Lambda as the execution runtime to run all of these bot clients concurrently. Compared to EC2, Lambda is a whole lot cheaper. You don't pay for them when they're not running. And they also pull up pretty much instantly. So no more waiting for 10 minutes to get a server, so they can run your load test for another 10 minutes. And they're also very easy to update as well. If you update your bot client code, just single push, few seconds later, bang, you've got a new version up and running. And with a minimum amount of optimization, we found that I can run this one Lambda invocation. Even though it's a very constrained execution environment, I can still run like 100 bots on one invocation alone. So trying to run load tests with, say, 10,000 bots, that just means invoking a function. What's 10,000 here for 10? Oh, 1,000 invocations. No, 100 invocations. I'm not going to go into details how this thing works. There's a blog post I will link at the end that you can go and read yourself. The thing I want to mention is that we now have a Jenkins build that we can easily go and trigger load tests, and we can also include it as part of our build pipeline as well. And at the end of every load test, we will get a nice report back that tells us the round trip time. In this case, the Lambda is running in US East, the Scale server is running in Ireland. We do this split just so that we introduce arbitrary latency between the two nodes. Otherwise, the number is going to be too good. We're trying to simulate what may look like real network latency-wise between the client on a mobile device on a server that's close to them. And once we have these numbers, we have a target that we can really focus our optimization toward, which is to optimize those 99th percentile latency numbers. If you want to read about it, I put a blog post together on our blog, which is tech.space8games.com, I believe. But anyway, follow the link. So yeah, with that, that's all I have. Tony, do you want to take some questions now with me?
Sure. Thanks so much.